It's always a pleasure. It's always a pleasure. It's like to be here even remotely. So it's the third time I've visited, I guess, Wisconsin. And so today I'll be talking about some of the work we've been doing. It's like on connecting sort of discrete mechanics with information geometry, some new directions in accelerated optimization, and the potential connections to machine learning. So this is in collaboration with sort of a number of my students. It's like Valentin Deriscu, who's been working with me. It's like on sort of particularly the accelerated optimization aspects. Jeremy Schmidt was a former student. And Jin Zhang is a professor of psychology at the University of Michigan, who's a collaborator on the information geometry aspects, and very generously funded by the National Science Foundation and by the Air Force. So let me try to give you a sense as to what the motivation for all of this is. So part of the goal is to develop, in some sense, a unification of information and mechanical systems. And this is motivated, if you will, by the implications for control systems. So of course, there's a lot of interest these days in what are called cyber-physical systems. These are physical systems or mechanical systems, which also, of course, obviously incorporate some sort of computational or, cybernetic aspect to it. And I think increasingly, it's like the control of these systems is hindered by the fact that traditionally one tends to think of these information theoretic aspects and the mechanical aspects as being disjoint. But the reality is that there's no separation of timescales between the information and the physical dynamics. And so ideally, it's like one would like to be able to formulate both the information theoretic and the mechanical aspects on equal footing in your modeling and in your simulation. So the way we're going to propose doing this is to relate information geometry and discrete mechanics. And what happens when you do that is that then you'll be able to realize the various machine learning algorithms as exact time H flows of dynamical systems on the space of probability distributions. And this allows you to have a unified treatment of what we're going to call information mechanical systems. So let me try to illustrate it's like where you have applications where there's no separation of timescales between the information layer and the mechanical system. So of course, it's like certainly in military applications, there's been a lot of interest in sort of these micro drones. And there is a view towards thinking of having large swarms of these drones. Okay. So in particular, these drones, it's like deployed often, it's like to perform reconnaissance inside buildings. But the problem is that these drones are very easy to disable. All you basically have to do is throw a blanket at one of these things. It's like, and obviously it's like they get caught in it. It's they'll crash. So what they basically need to do is that they need to fly extremely fast, something in the order of 10 meters per second or 22 miles per hour in order to avoid getting sort of these kind of countermeasures. It's like applied to them. So the problem, of course, is that it's like you have these drones moving very fast. It's like they're going past, for example, an open door. It's like, and they see it's like they're exposed to a new information flow, which is at the time scale which is comparable to the speed at which they're moving. So this really violates the separation of timescales assumption, which is intrinsic to this idea that the traditional approach where you sort of use the information theory, it's like to develop high level, say it's like planning task, and then you assume that the mechanical system is always capable of realizing that kind of trajectory generation. So anyway, so the main point basically is that information gathering and coordination of swarms of drones could potentially benefit from a continuous time treatment of learning. It's like where, again, it's like both the mechanical optimal control as well as the optimization in terms of a more learning theoretic task is treated on an equal footing. Okay, so let me sort of briefly say what information geometry is. So information geometry involves the use of differential geometric tools to describe the manifold or probability density functions. And in particular, there's a lot of interest in what are called, well, basically parametric families of probability densities. For example, the exponential family, it's like, and things like that. And so they form an embedded manifold in the ambient space of all density functions. And you can think of the coordinates it's like on this manifold as being the parameter values of this parametric family. So thinking of these things, and I should say that traditionally it's like, when one does learning task and optimization task, there's a tendency to treat these parametric representations, it's like as being the natural representation, it's like of the problem. And the problem with treating these problems that way is that parametric representation doesn't necessarily capture the differential geometric properties, it's like of the space of probability distributions. So treating this from a differential geometric perspective then allows you to investigate the intrinsic properties of these models as opposed to their parametric representations. And it naturally leads to geometric concepts like the metric, affine connections, and curvature. And these in turn out to be related to statistical issues like the asymptotic efficiency of maximum likelihood estimators. So it tells you something about the approximation properties, if you will, and that the approximation properties are in some sense, it's like constrained by geometric properties of the space of probability distributions you work with. Okay, so how is this then connected to machine learning? So one way to think of certain classes of learning algorithms is that you can think of them as optimization problems, where you're trying to find, in some sense, a distinguished element of this space of probability distributions that represents your knowledge of the system. And so, there's a sense in which you have a candidate probability distribution, and you want that somehow to give you predictions which minimize the mismatch with the data which you're given, okay? And so one way to measure that mismatch, if you will, are what are called divergence or contrast functions. And you can think of them as distance functions, which are in some sense asymmetric. So, so the divergence of A comma B is not necessarily equal to the divergence of B comma A, for example. And from a geometric perspective, what happens is that these divergence functions induce metrics, they induce connections, which allow you to define things like parallel transport. And then these differential geometric structures can then be used to construct optimization algorithms in the sense of optimization of manifolds. Okay, so and again, it's like it gives you a way to think of these optimization algorithms intrinsically. It's like in terms of the geometric properties as opposed in terms of the parametric representations. Okay, and then finally, it's like my main area of interest is in what is called discrete mechanics, and it provides a geometric structure preserving discretization of analytical mechanics, particularly Lagrangian and Hamiltonian mechanics. And the way we approach this is by looking at discrete variational principles. So the connection between, it's like mechanics, information geometry, and machine learning has to do with the fact that the divergence function, which you see in information geometry, has an interpretation as a discrete Lagrangian, which is a generating function of the symplectic maps. And this discrete Lagrangian plays a central role in discrete mechanics, the same way that the divergence function plays a central role in information geometry. And so that's really sort of the connection which we're going to attempt to leverage here. So in particular, this allows you to impart a mechanical interpretation to certain machine learning algorithms. And in so doing, it allows you to potentially think of these algorithms as, again, sort of discrete time flows of continuous systems, continuous mechanical systems defined on this information manifold. Okay, so that's sort of the high-level picture of what we have in mind. So let me sort of briefly tell you what a divergence function is. So a divergence function is basically, again, this sort of, scalar value function. It's like on 2 copies of the information manifold, and it has some regularity assumptions. It's always non-negative, right? And it's only equal if, the 2 points or the 2 points in the manifold are equal to each other. And then there are some properties about the partial derivatives. So I should say something about the notation here. The d sub I just means partial derivative with respect to the xi component, and then the comma j means that you're also taking this partial derivative with respect to the j component, but in the second slot. So before or after the comma refers to whether or not you're differentiating with respect to the first parameter or the second parameter. It's like in the divergence function. Okay, so there's some sort of compatibility condition here, and then this matrix, it's like of mixed partial derivatives is positive definite. Okay, so in particular, this thing is going to turn out to be something which generates something like a Riemannian metric on the problem. And yeah, so as I said, these divergence functions are pseudo-distance functions which are non-negative, but they don't need to be symmetric. So given one of these divergence functions, you can then extract certain different geometric objects from this. So in particular, you can extract a Riemannian metric, so this Gij, which, as I said, involves these mixed partial derivatives. And then you also have these affine connections, which involve these sort of triple derivatives. It's like of the divergence function evaluated along the diagonal. So let me sort of say something about connections if you're not familiar with it. So affine connections allow you to make sense of, it's like derivatives in a covariant way. So there are the objects which allow you to define covariant derivatives on manifolds. They're also the objects which allow you to transport vectors from one point in the manifold to another point on the manifold. And the basic idea behind this is that if you have curved space and you have tangent spaces to that, and you have vectors at, say, 2 points in the manifold, then there's no canonical way to identify those tangent spaces. And the affine connection gives you a way of identifying those two spaces in some sort of precise sense. So if you know something about Riemannian geometry, then you know that the Levi-Civita connection, which is sort of a very natural affine connection which arises in Riemannian geometry, has the property that it is torsion-free and it's metric compatible. So metric compatibility basically means that if you have a pair of vectors and you take the Riemannian inner product between those two things, and then you take those two vectors and you parallel transport that with respect to some connection, then that Riemannian inner product stays constant. It's like along that parallel transport. So something similar happens in the case of these pairs of affine connections. So here I said that they're torsion-free dual connections. And so the duality between these connections has to do with the following thing. So there are two different ways of parallel transporting vectors. And the point is that if you take the first connection and you parallel transport the first vector and you parallel transport the second vector with the second connection, then the Riemannian inner product that's like between those appropriately parallel transported vectors is the same, right? So in particular, obviously, the Levi-Civita connection is self-dual in some appropriate sense. But more generally, it's like you have these pair of connections which are dual respect to the inner product. Okay, anyhow, so you can write these dual connections as something involving the Levi-Civita connection. It's like, and something which is sort of a shift of T, which is called this skewness tensor, which is a symmetric covariant tensor. All right. And the reason why I tell you this is because what I'm going to later on, it's like talk about is sort of an inverse problem. So I've said that if I give you a divergence function, I can construct a Riemannian metric and this pair of dual connections from that. So one natural question to ask then is there a way, given a Riemannian connection and a pair of these torsion-free dual connections, to construct a divergence function which generates those things? Okay, so that's something which we'll return to at a later point. And it turns out there's a nice mechanical connection to this. Okay, so let me now perhaps say something specific about divergence functions and what are perhaps the most commonly used divergence functions. So one of the most commonly used divergence functions, which you might have heard of or might not have heard of, is the Bregman divergence. Okay, so these are class of divergence functions which come from a particular choice of a strictly convex function. So given a strictly convex function, you construct this object, and this is this family of divergence functions. So perhaps the most famous family, most famous element of the space of Bregman divergences is what's called the Kolbeck-Leibler divergence, or the KL divergence. So if you've done any machine learning, you've probably heard of KL divergences. And the KL divergence is a Bregman divergence where the strictly convex function in question is the negative Shannon entropy. And then, as I said, given the divergence function, there's an associated Riemannian metric. And the associated Riemannian metric to the KL divergence is the Fisher-Rao metric. Okay, so this is sort of very natural object that's been working with sort of probability distributions. And it's like when in doubt, that's what people use. Okay, so all right, so that's sort of the precursor. As I said, it's like this is the stuff on the information geometry. Now I'm going to give you a quick introduction to discrete mechanics, and then I will circle back and tell you how these things are connected to each other. So what I'm primarily interested in are a class of numerical methods known as geometric integrators. And so these are numerical methods which preserve geometric properties like symplecticity, momentum maps, as well as the nonlinear manifold structure, it's like the configuration spaces you might be working with. So in particular, it's like if you have a configuration space, which is a Lie group or homogeneous space, you might want to develop numerical methods which automatically stay on that. Okay. And the motivation for doing this is that they tend to result in numerical simulations with better long-time numerical stability and better qualitative agreement with the exact flow. And so one way to sort of see this, obviously, is that if you have geometric invariance, then the dynamics evolves on the level sets of these geometric invariants. And so if you have numerical methods which respect that, then typically it's like, you'll get, better long-term numerical results as a consequence of this. So let me try to say a little bit about what the approach we use to do this is. So as I said, it's like the main area I'm interested in is in analytical mechanics from Lagrangian and Hamiltonian mechanics. And there's a nice sort of intrinsic way of thinking about mechanics. Instead of thinking of it in terms of, say, Newton's second law, you can think of it in terms of what is called Hamilton's principle. And what Hamilton's principle basically says is that if you have an initial point and a final point, then the trajectory which the system actually takes is that which extremizes the action integral, which is the integral of kinetic minus potential energy. So if you write down the Lagrangian, the usual Lagrangian, which is quadratic kinetic energy minus potential energy, and you put it into this and you write down the corresponding equations, the corresponding Euler-Lagrange equations, which are the stationarity conditions for this variational principle, then you get something which basically says that the time derivative of the momentum is equal to the force exerted by the potential, which is, of course, Newton's second law. So it's a very nice way of describing, it's like equations of motion, because as is sort of fairly obvious from the way we formulate this, it is independent of the choice of coordinates. Okay. All right. So now we're going to try to discretize this, and the way we're going to try to discretize this is by replacing the action integral by things which are, for lack of a better term, pieces of the action integral. So instead of integrating over the entire time interval, I'm going to integrate it over a short time interval. All right. And I'm going to evaluate that action integral along a particular curve, which is a curve which satisfies the Euler-Lagrange boundary value problem, which is to say that this curve Q01 satisfies the Euler-Lagrange equations in the interior interval from 0 to h, and the boundary data associated that is given by this thing on the left-hand side, which is Q0, Q1. So given the initial point Q0 and the final point Q1, I find a curve which satisfies the Euler-Lagrange equations and which matches those endpoint conditions. And I evaluate the action integral on that, and that's what I call the discrete Lagrangian. Okay. So, and this is related in a relatively straightforward way to Jacobi's solution of the Hamilton-Jacobi equation. So this gives you a generating function for the exact time h flow of the Euler-Lagrange equations. So, the problem, of course, is that that's sort of a chicken and egg problem, right? And so in order to actually compute the what I call the exact discrete Lagrangian, you have to be able to solve the Euler-Lagrange boundary value problem. And if you can solve the Euler-Lagrange boundary value problem, you should just stop there. You're done, right? There's really no need to do anything else. So you might ask, what value is there? It's like this characterization, and the value is that even though that's not a computable object, it's helpful to know that it exists, because then you can think about approximating dynamics in terms of approximating this exact discrete Lagrangian instead of thinking about approximating the equations or what have you. And the second thing is that this characterization of the exact discrete Lagrangian then naturally lends itself to systematic discretizations, which are arbitrarily high order. So you can construct arbitrarily high order discretizations of the exact discrete Lagrangian, which will give you numerical methods again of arbitrarily high order. All right. So before I go on, let me say something about the equations you get from this. So the discrete Lagrangian, as I said, is something like a short sort of integral over a short period of time of the action. So if you sum it all up, right, you get something which approximates the action integral. So this sum of the discrete Lagrangian over a sort of sequence of pair of points, right, is an approximation of the total action. It's like over the entire time interval. And then the discrete Hamilton's principle is that the variation of this total action sum is stationary with respect to variations which keep the endpoints fixed. So this is sort of the obvious discrete time analog of the usual Hamilton's principle. And if you write down those stationarity conditions, then you get what are called the discrete Euler-Lagrange equations. And then here the D2 and D1 correspond to differentiating respect to the first or second slot. Okay. So if you look at this, you can think of as being a sort of a two-step method, right? So in the sense that given the current solution and the previous solution, it gives you the next solution. Okay, so it doesn't depend on just the data at one point, it depends on the data at 2 points. Okay, so you can think of it as describing it's like this sort of two-step method, if you will. But if you don't want to think of it as two-step method, you want to think of it as a one-step method. It is a one-step method in sort of phase space, right? So if you write the variables in terms of position, qk is position, and pk is momentum, then this is going to define a map from qk pk to qk plus 1 pk plus 1, which is then a one-step method. All right. So you might ask, well, what are some of the theoretical advantages of constructing a numerical method this way? And I think there are sort of two main things, right? The most important point is that you can analyze properties of the numerical method by analyzing properties of this discrete Lagrangian. And then there are essentially meta theorems which tell you that given these properties of discrete Lagrangian, your numerical method has certain properties. So the first one of these meta theorems is sort of the discrete Milford theorem. So in the continuous time case, Lagrangian and Hamiltonian mechanics have the property that if their Lagrangian Hamiltonian is invariant under some sort of group action, then there's an associated momentum map which is conserved. So there's something similar here. If your discrete Lagrangian is invariant under the appropriate group action, then there's a discrete momentum map which is preserved by the flow. So if you can construct a discretization which has the symmetry property, then you will automatically have a momentum preserving method. Okay, so that's the first observation. And then the second observation has to do with the error analysis. So instead of doing the error analysis in terms of the numerical method itself, you can do the error analysis in terms of the generating function. So the basic idea then is that you have this formal object, which is the exact discrete Lagrangian. And if you can show that the computable thing which you're working with approximates this exact discrete Lagrangian to a certain order of accuracy, then your numerical method, which are given by the discrete Lagrange equations, have the same order of accuracy. So, so again, it's often the case that doing this analysis at the level of the generating functions is much easier than trying to do the error analysis at the level of the full-blown numerical method. I should say that in addition to that, we also have certain results which tell you how to systematically construct computable discrete Lagrangians with a given order of accuracy, and they turn out to be related to sort of the best approximation properties of the function spaces you work with, for example. Okay. The other thing which I think is potentially important in context of learning and optimization is the fundamental role in which symplectic methods and Hamiltonian systems play in adjoint systems. Okay, so if you give me any system of differential equations, it doesn't have to be Hamiltonian, it doesn't have to have mechanical structure, any system of differential equations at all, and you compute the adjoint associated with this, which is basically the the variational equation, the dual of the variational equation, all right? Then the combination of the system of differential equations and the adjoint system has a Hamiltonian structure, even if the original system of differential equations does not have a Hamiltonian structure. And in particular, the idea of symplecticity in this setting is essentially encoding the standard relationship between the original variables and the adjoint variables. So if you break the symplecticity condition, you break all value it's like in computing the adjoint system. Okay. So why is this interesting? This is interesting because then it's like a symplectic discretization allows you to do an extremely important thing, which is that it allows you to have a discretization which commutes with the taking of adjoints. So, so you see this all the time when you're computing things like solutions to, it's like, 2-point boundary value problems or optimal control problems, or if you're trying to train a neural network, right? So if you try to train a neural network, the bottom line is that you have a bunch of knobs you get to turn. It's like there's an output or residual error which you're trying to minimize. Okay, so you want to compute essentially the sensitivity, it's like of the residual respect to the knobs, if you will. Okay, and the way you typically do this is you compute the solution of the adjoint system, but in the actual applications, it's like what you do is you do what is known as automatic differentiation, and that's because you might have you're really trying to compute the sensitivity, if you will, it's like of your discrete system or your deep neural network, all right, and then you have to do this sort of automatic differentiation in order to compute that sensitivity. Okay, so if the system it's like which you're describing is a continuous dynamical system instead, right, then there are sort of two ways to do it. You can either compute the sensitivity of the continuous system and then discretize it in some way, or you can look at the discrete system, which you're actually trying to compute the sensitivity of, and then compute its sensitivity. Okay, and the right way, in some sense, is to compute the sensitivity of the discrete system through something like automatic differentiation. But what this result is basically saying is that you can get the same result as automatic differentiation by discretizing the adjoint equations with a method which is symplectic. So what I mean by that, so you had the original equations, say the original equations are discretized with a recursive method, right? Then you have this adjoint system which has the original equations plus the adjoint equations. So you have to essentially discretize that system with a partition recursive method, where you use the original recursive method for the original set of equations, but you use a complementary recursive method for the adjoint equation, so that together that method is symplectic. And if you do that, then the numerical results you get are exactly equivalent to what you would have gotten if you had done automatic differentiation, up to machine precision, basically, right? So you know, it's a long story, but the basic idea then is that symplectic discretization gives you a way to avoid automatic differentiation in problems it's like which come from continuous problems. And all you have to do then is you have to discretize if you need continuous adjoint equations through an appropriate symplectic discretization. Okay. So anyway, so I think that's sort of something which I think is still underappreciated in the community, but I think has important implications, certainly in terms of learning and optimization. All right, so anyhow, so let me sort of get back to sort of what I alluded to earlier, which is that you can use this characterization of the exact discrete Lagrangian to construct sort of discretizations. So there's a nice variational characterization of the exact discrete Lagrangian, which is to say that you look at the action integral over classes of curves which are twice differentiable and which satisfy the boundary conditions, and you extralize over this class, and that's the exact discrete Lagrangian, and that's clearly equivalent to what we had seen before, because the stationarity conditions for this basically just give you the Lagrange equations. So this is equal to evaluating the action integral along a curve which satisfies the Lagrange equations and satisfies the boundary conditions, which is sort of the boundary value characterization I talked about earlier. But this variational characterization leads to sort of very natural class of Reed's discrete Lagrangians, where you replace this family of twice differentiable curves with a finite dimensional function space, and replace the integral with some sort of quadrature rule. Okay, so when you do that, it's like then there are a bunch again of meta theorems. It's like we say that if the approximation spaces you use, it's like have what is called a group equivariance property, and the continuous Lagrangian is invariant, then this Reed's discrete Lagrangian is group invariant, and then because of this discrete Nofus theorem, it's going to preserve some momentum maps. Okay, so this is a way to systematically construct momentum preserving methods. And this idea of group equivariance is very, very natural. So imagine you have a bunch of control points and you want to have a curve which goes through it, and that's your interpolation scheme. So what group equivariance means is that if you take those points and you transform it, say, by rotations, so you take all these points and you rotate them by a uniform rotation, and you look at the new interpolant which goes through that, you want the new interpolant to be related to the original interpolant by that same rotation. And if you can construct an interpolation scheme which respects that, then it is group equivariant. And it's like you can use that again to discretize things which are group invariant to get a discrete system which is again group invariant, and as a consequence momentum preserving. And so this is easy to do. It's like in sort of the ODE setting. It's a little bit more complicated in PDE setting, but there are ways to deal with that, which I won't go into. And then the other thing is this optimal rates of convergence. And so the basic idea is that if you construct a Reed's method out of a choice of a function space, then it's very natural to ask whether the numerical method you've constructed has this sort of optimal rate of convergence, which is to say that the numerical error you have is related, is bounded from above by some multiple of the best approximation error. So if that function space is capable of approximating the exact solution with respect to some norm at a particular rate, you would like that the numerical answer you get out of it, right, has an error which is bounded by some multiple of that best approximation error. And if you can, then this is sort of said to be optimally convergent. So anyway, so the basic idea then is that for certain classes of Lagrangians, right, you can show that these Reed's variational integrators are indeed ortho-optimal, and that if you were to do sort of a spectral type method where you fix the time intervals, but you you refine, say, the polynomial order, then you have a geometric rate of convergence. So that ends up being quite nice. So I think this gives you a very systematic way of relating it's like the error analysis of your numerical method with approximation theory. And I think that's an important thing to leverage. I mean, it's like oftentimes in numerical analysis, it's like being able to connect it's like the properties of your system. It's like with the approximation errors of the function spaces you work with is extremely critical. It gives you a systematic way of constructing numerical methods. Okay, so now let me sort of connect everything back to information geometry and sort of it's like tell you why it's like I think there's an interesting potential connection between discrete mechanics and information geometry. So earlier I had said that given a divergence function, there's an associated metric to it. Okay, and then in addition to that, the divergence function sort of looks like a generating function, right? It depends on two copies of the manifold. It gives you a real number. You can pretend it was a generating function like a discrete Lagrangian, and it will induce a symplectic map from that. So the divergence itself induces a symplectic map. Divergence induces a metric, and associated metric obviously is the geodesic flow to it. So you can ask yourself whether the time geodesic flow of the metric which is induced by the divergence function is related in some way, shape, or form to the symplectic map which is generated by the divergence function. And it turns out that it's always consistent. So if you take the divergence function and construct the symplectic map from it, it's always going to be a consistent discretization of the time h geodesic flow. Okay, so that's kind of interesting. But what's more interesting is that if that divergence function is a Bregman divergence, then that approximation is second order accurate. Okay, so that's the first thing. So if nothing else, it's like that means that you can use it's like the KL divergence to generate second order accurate approximations of the geodesic flow associated with the Fisher-Rao metric, just there and then. Okay. But the other thing is that, which I talked about, is this idea of canonical divergences, which is sort of the inverse problem. Given a metric and given a pair of affine connections, can you construct a divergence function which generates that specific metric and that specific pair of affine connections? And the way you do this, one way to do this, it's obviously not unique, okay? But one way to do this is to use Hamilton-Jacobi theory applied to this particular Lagrangian. So the Lagrangian is constructed by sort of a term involving the metric. So this is sort of like a kinetic energy associated with the metric we prescribed. And then there's sort of a cubic term, it's like which has to do with the skewness tensor. Okay, so this combination then gives you a Lagrangian, right? And if you construct the exact generating function associated with this, then you will get one of these canonical divergences. And in particular, you don't really need to construct the exact generating function. It's really sufficient to construct a second order accurate approximation, a Jacobi solution. But that's exactly the kind of thing, it's like the kind of questions we ask, right? If you have an exact generating function, how do you systematically construct high order discretizations of this? And so this problem then naturally fits into this framework of constructing good discrete Lagrangians, which I sort of talked about. Okay. All right. So the next thing then is, okay, given one of these, it's like divergence functions, how do you actually then incorporate data? And is there sort of a mechanical interpretation to certain machine learning algorithms? So one way to sort of think about this is that you can think of the dynamics, it's like on the space of probability distributions as trying to find, again, a good, it's like representative element of the space of probability distributions, which matches the data well, okay? So, and at the same time, you don't want the algorithm to go straight to the minimizer, it's like of this, it's like you want the thing to be updated in sort of a relatively smooth way. So that naturally suggests from a mechanical perspective that there are two terms which you would want to approximate. One of which is a potential term, which again measures the mismatch between the estimator and the actual data. And the other one is like a kinetic energy term so that there's some inertia to the system, okay? So that again, it's like these estimators don't bounce around, it's like too much, there is some sort of inertia, which takes into account, it's like what happens previously. So that's exactly what you do. You write down a discrete Lagrangian, okay? And then you have this term here, which involves the divergence function applied to two adjacent estimates, if you will. Okay, the estimate from sort of the prior estimate and then sort of the current estimate. And this sort of is morally a kinetic energy term, which penalizes very rapid changes in your estimator. And then, then there's another one, it's like, which is now sort of a data fidelity term. It's like a loss function, right? It measures the, distance between the new, it's like estimate, it's like, and what is sort of the data is telling you, okay? And so now you have this very nice, purely discrete time formulation of a very natural class of learning algorithms. It's like where you're trying to take the estimate, it's like as you get more and more data. So the data could be done, this kind of data analysis or data sort of estimation can be done sort of dynamically, right, where the data is changing. And then there's what is called backward error analysis, which then allows you to relate this discrete time algorithm with a continuous time system. So you can either now view certain classes of learning algorithms as continuous time dynamical systems, or you could stay in this discrete time framework and think of the learning, it's like as in discrete time, and then the mechanics can be viewed as being in discrete time through what we had talked about in terms of discrete mechanics. So in either case, there is a consistent framework where you can think of both systems, both the information dynamics as well as the mechanical dynamics, it's like on equal footing. Okay, and the hope is that we'll be able to develop then optimal learning strategies, which take into account the fact that, for example, your sensors are actual, they're mounted, it's like on robots, they're moving, you don't get the flexibility to take a sensor and just drop it, it's like somewhere, it's like 5 miles away, it actually has to move there, and you want to take that into account when you're thinking about these problems. Okay, so that's sort of the first part. And the next part has to do with optimization. And let me sort of again say why it's important and why it's natural to think about this in the context of learning, right? So it's sort of fairly clear, even in what we talked about so far, that it's like, again, many learning algorithms can be viewed as optimization problems, where you're trying to find some it's like distinguished element of a space of candidate models, right, which minimizes the loss or the mismatch, it's like with the data. Okay, so again, it's like you can think of learning problems as optimization problems, and it turns out you can also think of optimization problems as learning problems. And we'll, as we talk about this further, you'll see again that there's some sort of nice analogy between those two things. So, all right, so now I'm going to talk about what is called accelerated optimization. And so I'm going to consider some sort of optimization problem where you're trying to find the minimizer of some convex function in some convex domain. And obviously, because of the convexity, it's like you have a unique minimizer. So, and you probably know that, there are standard gradient type methods, it's like which you can develop to solve this problem. And the thing which is worth noting is that standard gradient methods converge typically at 1 over k, where k is the iterations. So they converge linearly in the iteration number. And what was interesting was that, Nesterov, it's like back in the 1980s, introduced what he called the accelerated gradient method, which is given here. And what was exciting about it was that this accelerated gradient method converged to the minimizer at a rate, instead of 1 over k, it converges to the rate of 1 over k squared. So this is what then became referred to as acceleration, okay? And what the other thing it's like Nesterov proved was that this 1 over k squared rate is actually optimal over methods which use only information about the gradient of f as successive iterates. And again, these standard gradient descent methods only achieve they go of 1 over k. Okay, right. So not only does the Nesterov accelerated gradient method, it's like achieve this 1 over k squared bound, it's like it's proved that this is optimal, at least for it's like just convex functions, right? I mean, it's like if you have stronger sort of assumptions about the regularity of the function, it's like then you can get faster rates of convergence. But in the worst case, it's like that's the bound. Anyhow, and that bound is optimal, and it's proved actually by actually constructing it's like a convex function, it's like which achieves that bound. Okay, so nevertheless, it's like there was a lot of interest. It's like as a consequence of this work, it's like on understanding acceleration and thinking about are there ways of constructing methods which achieve acceleration as well. So I should say that this result is asymptotic, right? So what's interesting is that, as we'll see later on, it's like in the results we show that even though you have this asymptotic sort of barrier, if you will, right? It's oftentimes the case that methods can perform better than this 1 over k squared rate, at least for moderate times, right? And oftentimes that's enough because you can get the error is sufficiently small that you can terminate before, say, the method goes unstable. It's like, or something bad happens, which then sort of limits to this sort of sort of asymptotic rate. It's like, which is proved by Nesterov. And the other thing is, of course, it's like that, it's like this asymptotic rate is also potentially pathological, right? I mean, it's like, so it's proved that it's the worst case thing. It's like, but it's quite possible that, on average case, it's like you could perform better. Anyhow, so one way it's like to approach this question of how to construct generalizations of the Nesterov method is sort of the approach which, it's like Sue, Boyd, and Candace, it's like sort of did, it's like back about 5 years ago now, where they studied, it's like the continuous limit of the Nesterov method, and they showed that it corresponds to this, fairly simple second order differential equation. Okay, and obviously it's like you have a force associated with the gradient of the cost function, and then you have sort of essentially a dissipative term, which sort of goes to zero. It's like as time goes to infinity. Okay, so that's kind of interesting, and you can show that this converges. It's like at in continuous time at a rate of 1 over t squared. It's like to the minimizer, which is sort of what you might expect. Okay, so what is interesting is that you can generalize this continuous formulation to achieve any rate of convergence. So instead of 1 over t squared, it's like you can achieve any 1 over t to the p rate of convergence, is like the continuous flow, and to the sort of global minimizer. And this was done by, it's like sort of a group around Michael Jordan at the University of California at Berkeley. And it involves, it's like this Bregman divergence, which we sort of earlier saw. It's like, so you have this Bregman divergence, and if the 2 points are close enough together, then this approximates the Hessian metric. It's like where the, it's like the metric is coming from this convex function, right? From the Hessian of the convex function. So anyway, given it's like this Bregman divergence, you can construct what is called the Bregman Lagrangian or the Bregman Hamiltonian. And there are a bunch of parameters here, alpha, beta, and gamma, all right? But there are specific choices of alpha, beta, and gamma. It's like which will have flows which converge at 1 over t to the p. So I'll talk about that in a little bit. So if you look at these expressions, so let's just take a second to look at these expressions, right? These look morally very, very similar to the things which we saw before, as where I sort of talked about discrete Lagrangians, which are candidates for approximating, it's like machine learning algorithms, right? So you have a divergence function applied to 2 points which are nearby to each other. So this is again like a kinetic energy like term. And then you have a term here which involves is like the cost function with appropriate scaling. So morally speaking, the 2 terms are exactly what you might expect them to be. There is a term involving the loss term or the data fidelity term. And then there's a term which again is like a kinetic energy between 2 adjacent points. Okay. So, all right, so under sort of certain, it's like assumptions, it's like under growth conditions, then, it's like the flow of this continuous time system, the flow of this continuous time system converges, it's like at a prescribed rate to the minimizer. And you can show this using sort of a Lyapunov function approach. And if you just want to construct something which scales like 1 over t to the p, then you can choose alpha, beta, and gamma to be these things here. Okay, and then the growth conditions are satisfied, and the Lagrange equation converges to the optimal value in big O 1 over t to the p. Okay, so all right, so what is interesting about this? Well, let me just look back at this Lagrangian Hamiltonian. So the thing which is interesting about this is that you have Lagrangians and Hamiltonians, and if you know something about Lagrangian Hamiltonian mechanics, you might think, oh wait, it's like aren't Lagrangian Hamiltonian systems energy preserving? And they are energy preserving only if the Lagrangian Hamiltonians are time independent. So the energy is in fact the Hamiltonian is the Nova quantity associated with time translational symmetry. So what happens here is that these Lagrangian Hamiltonians are no longer autonomous, right? They're non-autonomous, they're time dependent. And so that poses problems because most of the methods which have been developed, it's like assume implicitly that there's some sort of autonomy in the system. So how do we go about dealing with that? So as I said, because of these scaling terms, the Bregman Lagrangian Hamiltonian are time dependent. And so you have to be careful, because if you naively apply symplectic and variational integrators to such time-dependent systems, you oftentimes get very poor numerical results. Okay, so what I'm going to try to do instead is the following. So if I give you a Hamiltonian and I give you a particular rescaling of time, which is described in terms of this differential equation, which involves G, which is a monitor function, then you can write down a new Hamiltonian system, which is defined by this Poincare transform, right? Whose flow then is, it's like this reparametrization of the original flow. All right. So, so before I go on, let me sort of explain why that's potentially interesting in the context of non-autonomous systems. And it's because if this monitor function was just identically 1, then this is sort of a very roundabout way of essentially introducing another copy of time as now a dynamical variable, right? So it's the same thing one does. It's like when dealing with, which we teach in our differential equations class, it's like, convert a non-autonomous system into an autonomous system. We add, it's like a new time variable. It's like a new time variable is equal to the old time variable, right? And now it's like everything is now autonomous. So this is more or less one way to do this using Poincare transforms. And then you get these corresponding Hamilton's equations with these kind of initial conditions. All right, so what happens then is that you typically, the problem is that you typically obtain now a degenerate Hamiltonian. Okay, why is this significant? This is significant because so far when I talked about variational integrators and symplectic methods coming from that, I've always talked about this in the context of the Lagrangian side. Okay, and you probably know that, it's like under certain regularity assumptions, the Lagrangian and Hamiltonian formulations are equivalent. So the point, or the problem, if you will, is that if you have a degenerate Hamiltonian system, then there isn't necessarily a corresponding Lagrangian formulation of the problem. Okay, so why is this significant? This is significant, obviously, because all the methods which I talked about are based on the Lagrangian formulation. So in order to use this sort of Poincare transformed formulation, you need to construct variational integrators now on the Hamiltonian side. Okay, so that's something to just keep in mind. So as I said, it's like if you have this monitor function be identically 1, there's a degenerate Hamiltonian for which no Lagrangian analog exists. And this is sort of the candidate which we're going to try to use to convert the non-autonomous Hamiltonian formulation to the Hamiltonian, to a sort of an autonomous Poincare transform Hamiltonian. Okay, all right. So that's something to worry about. It's like, which we'll address that a little bit. And then the other thing is that as long as you have certain conditions, then the usual variational error analysis still holds, which particularly relates the, it's like order of the numerical method with the order of approximation of these discrete Lagrangians. Okay. All right. So as I sort of alluded to here, it's like you have to use Hamiltonian variational integrators. So that's something which we've developed. And time permitting, I'll say a little bit about that. And you can do this. So you can actually take these Poincare transform things and you can construct Hamiltonian variational integrators out of this. And in particular, we developed this 4th-order Hamiltonian Taylor variational integrator. And it's like these time-adaptive methods sort of perform much better. It's like they have better energy and better global behavior with dramatically lower cost. And what's surprising is that this actually is better even compared to things like Sturmer-Villei from a computational efficiency perspective. And if you know something about Sturmer-Villei, it's like that it's actually in practice very, very difficult to compete with because it's an explicit method with a lot of nice conservation properties, right? So, so nevertheless, it's like, from a computational efficiency perspective and quality assimilation perspective, these adaptive variational integrators are capable of doing a comparable, and in most cases, a better job. Okay, so let me now connect this back to these Bregman Hamiltonians. So what we're going to do is we're going to use what's going to happen is that we have a P Bregman Hamiltonian. It's like which has a convergence rate to the minimizer of big O 1/t to the P, and we're also going to do sort of a strange thing, which is that the family of P Bregman Hamiltonians have a scaling symmetry to that, which is to say that if you rescale time in a prescribed way, then you get the dynamics of a different P Bregman Hamiltonian system. So they're closed under the certain classes of time rescaling. And we're going to take advantage of this to essentially convert a high P Bregman Hamiltonian system, so they're closed under the certain classes of time rescaling. And we're going to take advantage of this to essentially convert a high P Bregman Hamiltonian system, so they're closed under the certain classes of time rescaling. And we're going to take advantage of this to Lagrangian system, Bregman Hamiltonian system, to a lower P Bregman Hamiltonian system, because it's somehow cheaper to compute the solution of the lower order Bregman dynamics, but you want to have the rate of convergence of the higher P Bregman Hamiltonian system. So that's sort of the rough idea. And you have some sort of monitor function which achieves that rescaling, and this generates this Poincare transformed Hamiltonian. Those details don't really matter, but let me sort of just say, you know, what the numerical results tell you. So if you do a direct discretization, which is the one where the monitor function is identically 1, and you just treat the, you know, it's like the P Bregman Hamiltonian as if it was the pre-Bregman P Bregman Hamiltonian, then you get, you know, it's like, you know, pretty good rates of convergence. But when you do this adaptive scheme where you do this time rescaling as well, instead of just this uniform sort of copy of time, then you actually have a faster rate of convergence. You know, so adaptivity seems to play an interesting role here. And this is the dependence of P in the adaptive approach. As you increase the P, again, it's like you have a faster rate of convergence, which is again consistent with what you expect from the continuous analysis. All right. And P0 is the one which is sort of you're rescaling the thing to. So you want P0 to be small. And again, it's like when P0 is small, it's like it seems to do, again, a better job. So there are a lot of things you can play around with here. You can choose, it's like P, which is, again, the order of the method, the order of convergence of the continuous flow you're trying to approximate. And then P0 is the sort of the rescaled thing which you actually implement the code in. Okay. All right. So that's kind of promising. It's like, and you can compare it to sort of non-symplectic adaptive methods. So you can compare it to sort of, you know, standard ODE 45 or ODE 23 in MATLAB, and you'll see that again, it's like these sort of, you know, sort of variational integrators seem to do a better job here. Okay, so the left one is the direct approach, right? So and then the right side is the adaptive approach. So it should mention that essentially, you know, direct versus adaptive doesn't make a difference when you're using a sort of adaptive Runge-Kutta method, and that's because the adaptive time stepping, it's like in ODE 45 and ODE 23 somehow already picked the right scaling. It's like for the time steps. So there's a slight improvement. Actually, it's not even clear. This actually seems to do worse, right? But obviously with Hamiltonian formulation, it's like it actually does sort of better. It's like with the adaptive approach. So again, it's like there's much we don't fully understand, but again, it seems suggestive that symplecticity plays an interesting role potentially, and that time adaptivity also plays a potentially interesting role here. And you can compare it to Nesterov. It's like, and Nesterov, it's like does a really horrible job. It's like compared to these adaptive variational integrators. All right, so I should say that, you know, more recently, it's like we've been studying, it's like the generalization of these kind of Bregman Lagrangians and Hamiltonians to Riemannian manifolds. So we have a paper which looks at the continuous time analysis of these things. It's like on Riemannian manifolds in sort of different classes of objective functions for the convex case, for the weakly quasi-convex case, and for the strongly convex case. And they have different Bregman Lagrangians and Hamiltonians, it's like which then achieve sort of, you know, nice rates of convergence for and something which is in preparation right now is trying to use these ideas. It's like to then construct accelerator optimization schemes on Riemannian manifolds, and this is based on a sort of a constrained variational integrator formulation. And again, the preliminary results are quite promising. This is the generalized eigenvalue problem, where you're not just looking for the you know, it's like the maximum eigenvalue, but sort of the, you know, the k largest eigenvalues, for example. And then there's this imbalanced orthogonal proscritus problem. It's like, which again has this very nice rate of convergence. So this is sort of a more practical engineering motivated application where you're trying to essentially infer essentially the poses like out of camera. It's like in the data. It's like, and so you can think of that as an optimization problem on the space of camera poses, which is manifold. And again, it's like this seems to do a really good job. So this is the prior thing. It's like with the mismatches, and then this is after the registration is done. Okay, so I don't really have much time, so let me just sort of say that the essential idea behind the Hamiltonian theory is sort of the fairly obvious thing. If you have a Hamiltonian, you Legendre transform to the Lagrangian, you compute the discrete Lagrangian, and you move back, right? So what we're going to do is that you take the exact generating function, you write down the Lagrangian in terms of the Hamiltonian. It's like with the Legendre transform. Okay, so this gives you then a type 1 generating function in terms of the Hamiltonian, but then you have to do a Legendre transform to what are called type 2 generating functions, which involves the shift to then give you a candidate exact type 2 generating function. And if you discretize that, then you get these Hamiltonian variational integrators. And you can show that this is equivalent to Lagrangian variational integrators when you have hyperregularity, which is to say that if there's a Lagrangian analog. Okay, so I will skip all of this and then just summarize by saying that information geometry plays an interesting role. It's like in providing a differential geometric interpretation of a certain class of machine learning algorithms. And what is interesting is the role the divergence function plays and its connection with various differential geometric structures and statistical manifolds. And what we showed was that this is related in some precise ways. It's like the discrete Lagrangians, and the problem of computing or constructing canonical divergence functions is again very closely related to the kind of approximation problems one studies in discrete mechanics. So given sort of machine learning, it's like an optimization algorithms, it's like you can relate these things, it's like to discrete mechanics on the space of probability distributions. And in particular with the accelerated optimization algorithms, which are based on Bregman Divergence and Hamiltonian, there's a very nice way of discretizing this using geometric discretizations, in particular using Hamiltonian versions of variational integrators, which are time adaptive. And so the upshot, if you will, is that we would like to leverage this analogy between mechanics, learning, optimization, and optimal control to apply the techniques of geometric numerical integration to obtain systematically new classes of algorithms. Okay, so that's what I basically wanted to say. Thank you.
Thank you very much. There's any questions from the audience?
I may have a few.
Sure.
I was a little bit lost in the literature when you said the Nesterov, the similarity method is 1 over k squared, and that's the optimal convergence rate. But
yeah.
Later on, this Jordan's paper seems to indicate there are faster results.
Yes, right. I should have been clear, right? So the Nesterov result is for discrete time algorithms, right? So discrete time, and then Jordan's result is for the continuous time flow, right?
Okay.
And but as you sort of see, it's like at least for short times, right? You have to be careful because this is sort of an asymptotic result, right? Which is to say that you want this to go all the way, it's like to the minimizer. But what you see from the numerics is that, while you're converging, but you're not yet converged to the minimizer, it is possible for you to have faster rates of convergence locally.
I see.
Okay, so even though there is this theoretical bound, which is true, it doesn't preclude the possibility that you can construct methods which behave better in practice than the Nesterov scheme, right? And in particular, it's like, as you see here, right, the Nesterov scheme still has the appropriate asymptotic convergence, but locally speaking, right, you have a much faster rate of convergence with these Hamiltonian methods. And then the other thing is that this is for just convex functions, right? So if you have stronger assumptions on the cost function, right, you can actually achieve faster rates of convergence. So this is also the reason why when we talk about the Riemannian manifold case, we had broken it up into these 3 cases, right? Because you can construct methods which behave much better if you assume, it's like if the function you have, it's like it has greater convexity properties, it's like, and you take that into account in constructing the method.
Okay. I do have a question regarding your Poincare transform. When you introduce this a little g to translate the non-autonomous to autonomous, do you have an optimal g?
Yeah, so let me say a little bit about that in the context of the P Bregman. So it depends on the problem, right? So it's just a monitor function, and it's it's like there are several ways to do this. One obviously very natural way is to do something like curvature, right? So for the example we had here, which was, I should have said, was for the Kepler problem, right? You have the sort of time adaptive method for different types of monitor functions. So that's something which you prescribe, right? So that's a design parameter. It's like in the algorithm, okay? And it's, again, fairly standard. It's like to do things like, say equipartition of error, right? So if you were to do this in the context of our refinement, it's like for a finite element method, right, on a sort of moving mesh finite element method, right, then you might want to move the, it's like the cell boundaries so that the residual error is uniformly distributed. It's like across cells, right? So that's a very, very natural choice, and you can construct those kind of monitor functions if you want. It's like by, say, looking at truncation errors. It's like in things like that. So that's something which we don't prescribe in the method. It's something which is given to us as part of the design process for the algorithm.
Okay.
Having said that, for the application to the Bregman Hamiltonian, there is a very natural rescaling of the problem. So basically, again, there's a rescaling. It's like from a P Bregman dynamics to a P0 Bregman dynamics, and the rescaling is sort of the obvious one because you know that in both cases there's this convergence. It's like at 1/t to the P. It's like to the minimizer. So just the natural scaling is T maps to T to the P over P0 or something like that, or maybe the other way around. I don't quite remember. Right, and that will sort of rescale one of the P Bregman dynamics to the other one. And so that's what is used here to construct this monitor function. So you take that rescaling and you differentiate it, and that's exactly that rescaling which you have here.
I see.
So yeah, so for that problem, there's a natural rescaling. It's like, and actually for the Kepler problem, there's also, you can also use, the various Kepler laws. It's like to construct natural rescalings of time, right? So, so in particular, the equal area, it's like property of one of the Kepler laws. It's like can be used to construct a time rescaling related to how far you are, say, from the center. It's like of the solar system.
So it's very problem dependent.
Yeah, it's very problem dependent, and it's a design parameter. There are other types of approaches which we've been studying. It's like which is based on sort of essentially energy considerations, right? So there's, if you look at this extended time formulation, it's like you can think of constructing choosing the time step by enforcing energy conservation property. I'm not sure that's the most relevant thing to study here in the context of the sort of the Bregman dynamics, just because it's dissipative, right? So right now we're trying to understand the relationship between the energy conservation of the Poincare transformed Hamiltonian with the energy dissipation of the original Bregman Hamiltonian dynamics, and to see whether or not, there's something which more or less says that, well, the total energy is conserved, but it's because the total energy is like the energy of the system plus maybe the work done by the dissipative terms, right? So if you could have something like that, then energy conservation would have interesting, precise implications, which you could exploit, particularly in the context of the convergence analysis using sort of Lyapunov type techniques. But that's still something which we still don't fully understand.
That makes sense. Yeah, thank you.
Yeah. You're welcome. Yes. Yeah, go ahead.
Yeah, hi. So I had a question, and this is more like, sort of practical, coming from something that has come up in like my own research. So so suppose you're given a Hamiltonian, which is which say, maybe you don't know if it's convex or Hamiltonians in physics, they're generally like quadratic in your momentum, but Hamiltonians in like which come up for chemical reaction network theory, they have they're like exponential in the momentum. So you have e to the p, or you might have e to the p1 minus.
That's right.
So making a
this is a partition function type form to it.
Yeah, so making a Legendre transform is not easy at all. But what would be interesting is to find like paths using this Hamiltonian, right? Like the corresponding Hamiltonian trajectories. So I'm wondering if like any of the techniques that you mentioned, which one would be the best place to sort of start like look at?
Right. Yeah. So I think as I said, Okay, so let me maybe show you the references. There is this paper here. So if you look 8, 9, and 10, these are a series of papers which talk about constructing variational integrators purely the Hamiltonian side. So if you're interested in, it's like applications to Hamiltonian systems, presumably if you were doing something like sampling or Markov chain Monte Carlo, right? Then, and you don't want to look at the Lagrangian analog because, as you say, the Legendre transform is horrendous and it's difficult to invert, then these methods will, stay purely the Hamiltonian side. You don't have to construct the corresponding Lagrange. You may not even exist, right? And these methods will give you symplectic methods, and they still have the nice properties that you can systematically construct a large class of algorithms from. Okay, so let me sort of say a little bit about one of the things, about this optimal rate of convergence thing, which is the following. That's if you have a problem which, say, has multiple time scales, right? Then one interesting way which we're studying now to construct good methods which allow you to take larger time steps than, say, the fast dynamics is to build, in some sense, the fast dynamics into the spaces you work with. So if you have something which is fast and slow, and the fast dynamics is a solid tree, but it's well approximated by, say, sines and cosines, then you might consider looking at shape functions which have sines and cosines in it instead of just polynomials. And the advantage of doing that is that then you can then take time steps which are much larger than, say, the, it's like the oscillation length, it's like of the fast dynamics, and it would still give you a, sort of a good numerical method for it. So put another way, it's like, this connection with approximation theory gives you a very systematic way to construct adaptive approximation spaces and construct numerical methods which are adapted to what you know about the system. Okay, so if you know something analytically about the fast dynamics, so say you have something with fast and slow dynamics, and you pretend that the slow dynamics is frozen, and what is left over is something which you can analytically solve or compute easily. You can then use that as like to construct a numerical method which is then adapted to that problem, which you again allows you to take large time steps for. And so I think that's, that's potentially, I think, quite promising. We also have methods which are based on sort of exponential type ideas. So if you happen to know exactly, if it turns out that that system is, how should I say this? If it turns out that your fast slow system can be viewed as a perturbation of a linear fast system, and you can compute the solution of the linear fast system exactly, then you can use that again to construct methods which are much more efficient and which is stable again for much larger time steps than which don't resolve the fast dynamics. And that's something which I didn't mention here, but it's like if you email me, I'll be happy to send you that paper as well. So in any case, there are a large class of methods which you don't necessarily need to know a whole lot about. It's like we spend a lot of time, developing the theory so that it's like there's a systematic prescription for you to construct these methods for your specific problem class.
Thank you.
So hopefully that helps you. Yeah.
So it's 3:30. Shall we thank
Yeah,
Melvin?
I think we should we should stop recording and let people go if they want. And if we still have audience interested, we should just keep the room open, right? If no one has still have time.
Yeah, sure. I'm happy to hang around. It's like any questions offline. It's like, well.